In 1964, a Soviet astrophysicist named Nikolai Kardashev created a scale that would forever change how we think about advanced civilizations. He had no idea that 61 years later, in 2025, we'd have fusion reactors producing net energy gain, data centers consuming nearly 4% of global electricity, and space-based solar arrays becoming reality. The Kardashev scale remains our best framework for measuring civilizational progress as humanity faces its greatest energy transition in history. The question that's keeping scientists up at night: are these breakthroughs actually moving us up the Kardashev scale, or are we still hopelessly primitive? To answer that, we need to examine what Kardashev actually predicted and how dramatically our world has changed since he first sketched out his vision. The original vision versus today's reality. When Kardashev sketched out his civilization scale in 1964, he was looking at a world where the most advanced computer filled an entire room and had less processing power than a modern smartphone. The Soviet Union had just put the first woman in space, and the idea of carrying a device in your pocket that could access all human knowledge would have sounded like pure fantasy. Kardashev's vision was remarkably simple. Civilizations advance by harnessing more energy, and we could measure that advancement through three distinct types. Type 1 civilizations would control all the energy reaching their planet from their star. Type 2 would harness the entire energy output of their star itself. Type 3 would command the energy of an entire galaxy. Clean, straightforward, and focused entirely on raw power consumption. His timeline assumptions reveal just how different 1964 looked from our current reality. Kardashev figured it would take humanity several thousand years to reach Type 1 status, based on the energy consumption patterns he observed in the mid-1960s. He was watching a world powered almost entirely by coal, oil, in the early stages of nuclear fission. The concept of distributed energy generation didn't exist in his framework. Neither did data centers, which grew by 20% in 2024 and now account for roughly 4% of global electricity generation growth. Space commercialization wasn't even a distant dream when government space programs were still figuring out basic orbital mechanics. What Kardashev couldn't have predicted was the explosive development of technologies that don't fit neatly into his energy-focused categories. He envisioned civilizations advancing through brute force energy accumulation, but he never considered how information processing, global connectivity, or artificial intelligence might reshape the entire advancement equation. The global internet has created unprecedented coordination capabilities, connecting billions of minds in ways that transcend physical energy limitations. Renewable energy grids now span continents, sharing power across vast distances in patterns that would have seemed impossible to a Soviet scientist working within national boundaries. The three-tier system itself starts to look oddly rigid when you examine what we've actually built by 2025. Kardashev's Type 1 civilization was supposed to control planetary energy, but he was thinking about massive centralized power systems, probably nuclear, that would dominate entire continents. Instead, we've created distributed networks of solar panels, wind turbines, and energy storage systems that operate more like biological systems than the industrial megastructures he imagined. Over 250 gigawatts of rooftop solar now feeds excess energy back to grids worldwide. Electric vehicles serve as mobile energy storage units. Smart grids automatically balance supply and demand across regions using artificial intelligence. The space commercialization boom has created another category that doesn't map onto Kardashev's original framework. Companies like SpaceX are launching rockets at costs that would have been unthinkable in 1964, while others are seriously planning asteroid mining operations in space-based solar power systems. These developments blur the line between Type 1 and Type 2 civilizations in ways Kardashev never anticipated. If we're harvesting solar energy in space without atmospheric interference, are we still a Type 1 civilization, or have we moved partway toward Type 2 by directly accessing stellar energy? Perhaps most significantly, Kardashev's focus on raw energy consumption missed entirely how efficiency improvements could change the advancement equation. Modern LED lights use 80% less energy than the incandescent bulbs of 1964 while providing better illumination. Electric vehicles achieve roughly 90% efficiency compared to just 25% for combustion engines. Computer processors now perform billions more calculations per watt than their 1960s ancestors. These efficiency gains mean we're getting more civilizational capability per unit of energy, potentially reaching Type 1 functionality without hitting Type 1 energy consumption numbers. The artificial intelligence revolution presents another challenge to Kardashev's framework that he never could have foreseen. AI systems now consume enormous amounts of energy for training and operation, with some estimates suggesting that training a single large language model uses as much electricity as hundreds of homes consume in a year. But these same AI systems are simultaneously optimizing energy grids, accelerating scientific research, and solving engineering problems that could unlock entirely new energy sources. Should this energy consumption count as civilizational advancement or as waste? Kardashev's scale provides no guidance for this question. Climate change adds another layer of complexity that wasn't part of Kardashev's original thinking. In 1964, the idea that energy consumption itself could threaten planetary stability wasn't on anyone's radar. Environmental concerns were local and immediate, not global and existential. Now we're racing to increase our energy capacity while simultaneously transforming our energy sources to avoid catastrophic climate impacts. This creates a tension between Kardashev's vision of ever-increasing energy use and the practical requirements of planetary survival. The emergence of fusion energy as a practical technology creates the most direct challenge to Kardashev's timeline. He assumed that reaching Type 1 status would require massive scaling of existing energy sources, but fusion promises energy densities that could accelerate the timeline by centuries. The National Ignition Facility's achievement of fusion ignition in 2022, followed by multiple successful replications, suggests that we might reach Type 1 energy capacity far sooner than Kardashev predicted, but through a completely different technological path. All of these developments point toward a fundamental question that Kardashev couldn't have anticipated. Are we following his predicted path of civilizational advancement, or have we discovered entirely different routes to the same destination? The evidence suggests we're not just ahead of schedule or behind schedule, but operating on a completely different trajectory that makes his original timeline irrelevant. We're building a Type 1 civilization that looks nothing like what he envisioned, using technologies he never imagined, through social and economic structures that didn't exist in his world. But to understand whether we're actually making progress, we need to look at the numbers themselves, where humanity actually stands in 2025. The current data reveals humanity's position with startling precision. We consumed nearly 650 exajoules of energy in 2024, placing us at approximately 0.75 on the Kardashev scale. That represents a climb from 0.73 just 2 years ago, marking the fastest advancement rate in human history. To reach Type 1 status, we need to harness roughly 174,000 terawatt hours annually, equivalent to about 10 to the power of 17 watts of continuous power. Our current global energy consumption sits at around 180,000 terawatt hours when including all forms of energy use, meaning we're operating at roughly 75% of Type 1 capacity. Carl Sagan's refined logarithmic scale provides a more nuanced view of our progress, and the 2025 data reveals fascinating patterns. His formula accounts for not just raw energy consumption, but also the rate of increase and efficiency improvements. Using Sagan's calculations with current consumption figures, we've moved past the 0.73 mark that many sources still cite from older data. The acceleration in energy demand that occurred in 2024, with global consumption growing by 2.2% compared to the 1.3% annual average from 2013 to 2023, represents a significant uptick in our advancement rate. This growth pattern suggests we might reach 0.8 on the scale within 5 years if current trends continue. The composition of our energy consumption has shifted dramatically from what earlier Kardashev scale calculations assumed. Traditional assessments focused primarily on fossil fuel consumption and basic electricity generation, but our 2025 energy landscape includes massive data centers, electric vehicle charging networks, cryptocurrency mining operations, and artificial intelligence training systems that didn't exist in meaningful quantities even a decade ago. The IEA's Global Energy Review 2025 shows that electricity demand alone grew by 4.3% in 2024, with the largest absolute increase ever recorded outside of economic recovery years. This electrical consumption represents a more advanced form of energy use than the thermal energy that dominated earlier calculations. Energy efficiency improvements create a measurement problem that makes our true advancement level harder to pin down. Modern LED lighting systems use 80% less energy than incandescent bulbs while providing superior illumination. Electric vehicles convert energy to motion with 90% efficiency compared to 25% for internal combustion engines. Heat pumps now achieve coefficients of performance above 4.0, meaning they move 4 times as much heat energy as the electrical energy they consume. These efficiency gains mean we're achieving Type 1 civilization capabilities while using less energy than traditional calculations would suggest necessary. The distributed nature of renewable energy generation challenges the traditional centralized power models that Kardashev's scale assumes. Instead of massive power plants feeding into continental grids, we've built millions of small generation points that collectively provide enormous capacity. In 2024, renewable sources and nuclear power provided 80% of the growth in global electricity generation, with renewables alone supplying 32% of total generation. New renewable installations reached record levels for the 22nd consecutive year, with approximately 700 gigawatts of total renewable capacity added in 2024, nearly 80% of which was solar photovoltaic systems. This distributed approach means our energy infrastructure operates more like a biological network than the industrial megastructures that defined earlier advancement models. Expert opinions on our current classification reveal significant disagreement about how to measure progress in the modern era. Some researchers argue that our digital infrastructure and global connectivity represent advancement beyond what raw energy consumption numbers suggest. Others contend that energy waste and inefficient consumption patterns actually set us back from where the numbers indicate. The debate centers on whether a civilization should be measured by its peak energy capacity, its average consumption, its efficiency ratios, or some combination of all 3 factors. Space-based energy collection attempts add another layer of complexity to our current rating. The International Space Station generates about 84 kilowatts of power from its solar arrays, and various experimental satellites have tested wireless power transmission back to Earth. While these efforts represent tiny fractions of global energy consumption, they mark humanity's first steps toward directly harvesting solar energy in space without atmospheric interference. Some researchers argue that any space-based energy collection should count as movement toward Type 2 status rather than Type 1, since we're accessing stellar energy directly rather than just planetary energy. The energy waste question presents the most challenging measurement problem for assessing our true advancement level. Global energy systems waste approximately 30% of all energy produced through inefficient transmission, heat loss, and poor utilization. Cryptocurrency mining operations consume more electricity than entire countries while producing no physical goods. Data centers storing rarely accessed information consume massive amounts of power for questionable civilizational benefit. Different approaches to this calculation can shift our rating by several decimal points. China accounted for more than half of the global increase in electricity demand in 2024, but growth was broad-based with a 4% increase in other emerging and developing economies. This uneven development pattern creates another measurement challenge since different regions operate at vastly different efficiency levels and with different energy sources. Some areas have achieved near Type Ally energy densities through advanced nuclear and renewable systems, while others still rely heavily on coal and inefficient distribution networks. The integration of artificial intelligence into energy management systems represents advancement that doesn't fit neatly into traditional energy consumption metrics. AI systems now optimize power grid operations, predict energy demand patterns, and coordinate renewable energy storage across continental scales. These systems reduce overall energy waste while enabling more complex energy utilization patterns. However, the AI systems themselves consume enormous amounts of energy for training and operation, creating a feedback loop where advancing technology both increases and optimizes energy consumption simultaneously. Using 2025 data, humanity appears to be progressing faster than most predictions suggested possible. The combination of renewable energy scaling, efficiency improvements, and AI-optimized systems has accelerated our advancement rate beyond historical trends. We might be achieving Type 1 civilization functionality while consuming less energy than the scale traditionally requires. Or we might be consuming Type 1 levels of energy while achieving less civilizational capability than expected. The 2025 data suggests we're in uncharted territory, where traditional measurement methods no longer provide clear answers. But there's one technological breakthrough that could change everything about these calculations and compress our timeline to Type 1 status by decades. The fusion revolution that changes everything. Fusion energy represents something far more profound for the Kardashev scale than simply another power source option. Unlike every energy technology that came before it, fusion offers energy densities that could theoretically compress our timeline to Type 1 civilization from centuries down to decades. The reason lies in the fundamental physics. Fusion reactions release roughly 4 million times more energy per unit mass than chemical combustion, and about 4 times more than nuclear fission. This energy density difference isn't just incremental improvement, it's a complete transformation of what's possible for planetary energy systems. TAE Technologies achieved a breakthrough in 2024 that fundamentally changes how we think about fusion reactor design and deployment timelines. Their new approach streamlines plasma formation, enhancing efficiency, reducing complexity and cost, and accelerating the path to net energy and commercial fusion power. The innovation centers on their field, reverse configuration technique, where the plasma self-organizes and creates its own magnetic field. This reduces the need for external magnets and makes the device more power efficient. An FRC-based machine can achieve up to 100 times more fusion power output than a typical tokamak of the same magnetic field strength and plasma volume. TAE's new machine, called Norm, uses neutral beam injection to produce a hot, stable plasma while reducing the machine size, complexity, and cost by up to 50%. This represents a direct path toward economic competitiveness that previous fusion approaches couldn't match. Norm has validated operating modes and components to be used on Copernicus, their next-generation reactor prototype. Copernicus is expected to demonstrate net energy generation using TAE's advanced beam-driven approach before the end of the decade, followed by Da Vinci, their first prototype power plant in the early 2030s. The timeline compression becomes even more dramatic when you consider parallel developments in fusion reactor design methodology. Researchers at the University of Texas at Austin, Los Alamos National Laboratory, and Type 1 Energy Group developed a new method for designing fusion reactors that runs up to 10 times faster than previous approaches while matching the accuracy of full-scale simulations. This technique enables engineers to design more efficient fusion reactors, particularly stellarators, at a pace previously thought impossible. The ability to model and refine fusion reactors more rapidly drastically reduces design cycles and costs, potentially accelerating the entire fusion development timeline. Meanwhile, the French West tokamak reactor set a new record for sustaining ultra-hot plasma, maintaining fusion conditions for 1,337 seconds while reaching temperatures of 50 million degrees Celsius. This 22-minute duration surpassed China's East tokamak record by 25%, demonstrating that sustained fusion reactions are becoming routine rather than exceptional. The achievement proves that fusion plasma can be maintained for operationally meaningful periods, addressing one of the key technical hurdles for commercial fusion power. When you examine fusion energy density against Kardashev's original expectations for Type 1 civilizations, the numbers become staggering. A single fusion power plant occupying the same footprint as a large coal facility could theoretically produce 10 to 20 times more energy. The fuel requirements are equally transformative. Deuterium can be extracted from seawater, and tritium can be bred from lithium, making fusion fuel effectively unlimited on planetary scales. This abundance means that Type 1 energy capacity could be achieved without the massive resource extraction and transportation networks that current energy systems require. The geopolitical implications of fusion mastery create entirely new dynamics for civilizational advancement. Unlike fossil fuels, which concentrate power in resource-rich nations, or even renewables, which favor regions with optimal wind and solar conditions, fusion energy could theoretically be deployed anywhere on Earth with equal effectiveness. This democratization of energy production could eliminate energy scarcity as a source of international conflict while enabling rapid development in regions that currently lack abundant energy resources. However, fusion also introduces new tensions around technological leadership. China's aggressive investment in fusion research suggests they're pursuing energy abundance through multiple pathways simultaneously. The competition isn't just about having fusion technology, but about scaling it fast enough to maintain civilizational leadership. a fusion-powered civilization that reaches Type 1 status decades ahead of its competitors gains advantages that could persist for centuries. The question of whether fusion represents a shortcut to Type 1 status reveals the complexity of modern civilizational advancement. Fusion certainly provides the energy density needed for Type 1 capacity, but deploying fusion at planetary scale requires manufacturing capabilities, material science, and distribution infrastructure that don't exist yet. The reactors themselves need specialized materials that can withstand neutron bombardment for decades. The tritium breeding systems require lithium processing at scales never attempted. The electrical grid infrastructure needs complete rebuilding to handle the massive, consistent power outputs that fusion plants will provide. Private fusion companies are attempting to circumvent traditional roadblocks by developing smaller, modular reactor designs that could be deployed more quickly than massive centralized plants. TACE approach with hydrogen boron fuel produces no neutron radiation, potentially simplifying regulatory approval and operational safety requirements. Other companies are pursuing different fusion approaches that could be manufactured in factories rather than constructed on-site like traditional power plants. The economic dynamics of fusion deployment could reshape global energy markets faster than the technology itself develops. Once fusion plants prove economically competitive with other energy sources, the investment capital available for scaling could dwarf anything seen in renewable energy deployment. Unlike solar and wind, which face intermittency challenges, fusion provides consistent baseload power that can replace fossil fuel plants directly. Fusion isn't just solving our energy crisis. It's potentially compressing the timeline to Type 1 civilization by several decades through sheer energy abundance. However, this acceleration only happens if we can overcome the scaling challenges while maintaining the international cooperation necessary for planetary energy integration. The technology is advancing faster than the institutions needed to deploy it, creating a bottleneck that could determine whether fusion truly accelerates our civilizational advancement. But fusion isn't the only technology that could transform our energy equation. There's another approach that sidesteps terrestrial limitations entirely, and it's advancing faster than most experts predicted. Space-based solar, the game changer nobody saw coming. Space-based solar power systems are collecting energy at orbital altitudes where atmospheric interference doesn't exist. Japan's Ohisama project represents the most advanced operational demonstration, beaming approximately 1 kilowatt of power from a small satellite at 400-kilometer altitude directly to Earth-based receivers in 2025. This might sound modest compared to gigawatt-scale fusion reactors, but the significance lies in proving that wireless power transmission across hundreds of kilometers actually works in practice. The mission builds on successful ground-based wireless transmission tests and aircraft-based demonstrations, creating a complete proof of concept for orbital energy systems that moves beyond theoretical possibility into operational reality. The United States has committed unprecedented resources to space-based solar development, with Northrop Grumman receiving a $100 million partnership with the U.S. Air Force Research Laboratory specifically for advanced space solar technology. An additional $17.5 million collaboration between Northrop Grumman and Caltech focuses on the Space Solar Power Initiative, with the explicit goal of generating electricity at costs comparable to current terrestrial sources. These funding levels indicate that space-based solar power has moved from experimental curiosity to strategic national priority, with military and civilian applications driving accelerated development timelines. Orbital energy collection fundamentally changes the Kardashev calculation framework in ways that traditional energy assessments miss entirely. When solar panels operate in space, they collect solar energy directly without atmospheric filtering, whether interference or day-night cycles. Earth's atmosphere blocks roughly 30% of incoming solar radiation, while space-based collectors receive the full solar spectrum at maximum intensity 24 hours per day. This means that identical solar panel technology produces approximately 8 to 10 times more energy in space than on Earth's surface. The efficiency multiplication effect means that relatively modest space-based installations could provide energy equivalent to massive terrestrial solar farms. The efficiency gains become even more dramatic when you account for optimal positioning and tracking capabilities. Space-based solar arrays can maintain perfect perpendicular orientation to the sun throughout their orbital period, maximizing energy capture at all times. They experience no weather degradation, no dust accumulation, and no seasonal variation in solar angles. Ground-based solar installations typically operate at 15% to 20% capacity factors due to weather and day-night cycles, while space-based systems can theoretically achieve capacity factors approaching 90%. This efficiency difference essentially multiplies available energy by a factor of 4 or 5 compared to terrestrial installations of identical size. Infrastructure challenges for beaming power back to Earth present both technical hurdles and opportunities for breakthrough innovations. The wireless power transmission system converts collected solar energy into microwaves, focuses them into precise beams, and transmits them to ground-based receiving stations called rectennas. These rectennas then convert the microwave energy back into electricity for grid distribution. The precision required for this process demands satellite positioning accuracy measured in centimeters and beam focusing technology that can maintain power density across atmospheric transmission distances. Current demonstrations achieve transmission efficiencies around 85%, but scaling to commercial power levels requires maintaining that efficiency across much larger systems. Competing national space solar programs create geopolitical tensions that could determine which civilization reaches Type 1 status first. China has announced ambitious space-based solar power development programs targeting multi-gigawatt orbital installations by 2035. Their approach combines space manufacturing capabilities with heavy-lift launch systems to construct solar arrays directly in orbit rather than launching pre-built panels from Earth. This manufacturing approach could enable solar collection systems with areas measured in square kilometers, providing power outputs comparable to traditional nuclear plants. The nation that achieves large-scale space-based solar power first gains strategic advantages that extend far beyond energy independence. Space manufacturing capabilities enable solar collection arrays of unprecedented scale and sophistication. Rather than launching finished solar panels, future space-based power systems can manufacture photovoltaic materials in zero gravity using asteroid-derived raw materials. Space-based manufacturing eliminates weight restrictions and size constraints that limit terrestrial solar panel production. Orbital factories could produce solar panels with perfect crystalline structures impossible to achieve under Earth's gravity, potentially achieving conversion efficiencies above 40% compared to 20% for typical terrestrial panels. The combination of perfect materials and unlimited scale could enable space-based solar installations with power outputs measured in terawatts rather than gigawatts. Space-based solar power could leapfrog traditional renewable energy limitations in ways that transform global energy access patterns. Unlike wind and solar installations that require specific geographic conditions, space-based power can beam energy to any location on Earth's surface. Remote regions, disaster-stricken areas, and developing nations could receive abundant clean energy without building extensive grid infrastructure. Military applications include powering remote bases, ships at sea, and long-endurance aircraft without fuel supply chains. This geographic flexibility means that space-based solar could provide energy equity across regions that current renewable technologies cannot serve effectively. The economic dynamics of space-based solar deployment depend heavily on launch costs and space manufacturing capabilities. SpaceX's reusable launch systems have reduced payload delivery costs from $10,000 per kilogram to under $3,000 per kilogram, making large-scale space construction economically feasible for the first time. Further cost reductions through fully reusable heavy-lift vehicles could bring space-based solar power to economic parity with terrestrial renewable energy within the next decade. The key breakthrough comes when space-based installations produce more energy per dollar invested than equivalent terrestrial systems, accounting for their superior efficiency and continuous operation. Space-based solar power represents humanity's first step toward truly planetary-scale energy management rather than simply another clean energy option. Unlike fusion reactors or terrestrial renewables, space-based solar systems operate at the boundary between planetary and stellar energy collection, blurring the line between Type 1 and Type 2 civilizations. The technology demonstrates our ability to harvest solar energy directly in space and distribute it globally on demand, providing the kind of energy control that Kardashev envisioned for advanced civilizations. This capability could bring Type 1 status within realistic reach by enabling energy abundance that transcends geographic and temporal limitations. But there's another technology that's simultaneously accelerating and complicating our path to advanced civilization, consuming unprecedented amounts of energy while potentially providing
AI
the intelligence needed to unlock these
Artificial
very
intelligence
sources. Creates the most complex energy equation in human history. AI systems now consume energy at rates that would have been unimaginable just 5 years ago, yet these same systems are simultaneously solving the engineering challenges that could unlock unlimited clean energy. This paradox sits at the heart of our civilizational advancement, creating a race between AI's energy appetite and its problem-solving capabilities. The massive energy consumption of AI training and inference in 2025 represents a fundamental shift in how we use electricity on a planetary scale. Training a single large language model now requires approximately 1,000 megawatt-hours of electricity, equivalent to the annual consumption of 90 average American homes. GPT-4's training consumed an estimated 50,000 megawatt-hours, while newer multimodal AI systems require even more energy for their expanded capabilities. The inference phase, where trained models actually answer questions and perform tasks, adds another layer of continuous energy demand. Every ChatGPT conversation, every AI image generation, every automated decision made by AI systems requires computational power that translates directly into electricity consumption. Data centers have transformed from specialized facilities into some of the largest energy consumers on the planet, fundamentally altering global electricity demand patterns. The installed capacity of data centers worldwide increased by an estimated 20%, or approximately 15 gigawatts, with the United States and China leading this expansion. These facilities now consume roughly 4% of global electricity production, a figure that continues climbing as AI workloads expand. Google's data centers alone consumed 24 terawatt-hours of electricity in 2023, more than many entire countries use annually. Microsoft's data centers used 25.4 terawatt-hours in the same period, representing a 30% increase from the previous year, driven largely by AI model training and deployment. The power sector experienced a significant surge in global energy demand in 2024, with electricity demand increasing by 4.3%, nearly double the overall energy demand growth. The Deloitte 2024 Renewable Energy Industry Outlook emphasizes that the training and use of generative AI could increase data center demand for clean electricity by a factor of 5 to 7. This acceleration means that AI is not just consuming more energy, but consuming it at exponentially increasing rates that challenge our ability to scale clean energy production fast enough to keep pace. However, AI provides efficiency gains in energy management and distribution systems that potentially offset its own consumption through smarter resource utilization. Machine learning algorithms now optimize power grid operations in real time, predicting demand fluctuations with accuracy levels that human operators cannot match. These systems reduce energy waste by automatically balancing supply and demand across continental power grids, potentially saving 10% to 15% of total electricity consumption through improved efficiency. AI-driven predictive maintenance systems prevent equipment failures that would otherwise waste energy through system inefficiencies and emergency repairs. AI's role in optimizing renewable energy grids and storage systems creates multiplicative effects that extend far beyond simple efficiency improvements. Neural networks now predict wind patterns and solar irradiance with precision that enables renewable energy systems to operate at maximum efficiency. AI systems coordinate battery storage across thousands of installations, creating virtual power plants that can respond to grid demands faster than traditional power plants. These coordination capabilities mean that renewable energy systems can provide reliable baseload power despite their intermittent nature, removing one of the primary barriers to renewable energy scaling. AI might help solve fusion engineering challenges and space-based solar deployment in ways that could revolutionize our timeline to Type 1 status. Machine learning systems are already optimizing plasma containment in experimental fusion reactors, identifying magnetic field configurations that human engineers might never discover through traditional trial and error approaches. AI models trained on fusion physics data can predict plasma instabilities milliseconds before they occur, enabling real-time control systems that maintain stable fusion reactions for extended periods. These capabilities could compress the development timeline for commercial fusion power from decades to years. Space-based solar power deployment presents complex orbital mechanics and beamforming challenges that AI systems excel at solving. Neural networks can optimize satellite positioning for maximum energy collection while maintaining precise beam focus for power transmission to Earth. AI systems can coordinate fleets of space-based solar collectors, automatically adjusting their configurations as orbital positions change throughout their operational periods. These coordination capabilities could enable space-based solar installations to operate at efficiency levels that would be impossible with human control systems alone. The potential for AI to discover entirely new energy sources or collection methods represents perhaps the most significant long-term impact on our civilizational advancement. Machine learning systems are already identifying new materials for solar panels, battery storage, and fusion reactor components through computational screening of millions of possible combinations. AI has discovered new superconducting materials, optimized thermoelectric generators, and identified novel approaches to energy storage that human researchers might not have conceived. These discoveries could lead to breakthrough technologies that fundamentally change our energy landscape in ways that current projections cannot account for. The economic dynamics of AI energy consumption create feedback loops that could either accelerate or constrain our progress toward Type 1 civilization. AI systems that optimize energy infrastructure generate economic value that can fund further AI development and energy system improvements. However, the high energy costs of AI operation could also make these systems economically unsustainable if clean energy scaling doesn't keep pace with demand growth. The balance between AI's energy consumption and its economic productivity will likely determine whether AI represents a net positive or negative factor in our civilizational advancement. AI represents a double-edged sword in humanity's path to Type 1 civilization, consuming energy at unprecedented rates while simultaneously providing the intelligence needed to unlock the energy sources that could make Type 1 status achievable. The resolution of this paradox depends on whether AI's problem-solving capabilities can develop new energy technologies faster than AI's own energy consumption grows. Yet even if we solve the technical challenges of fusion power, space-based solar arrays, and AI optimization, we face an entirely different kind of obstacle that might prove even more difficult to overcome: the planetary cooperation problem. The coordination challenges that emerge when nations attempt large-scale energy projects reveal why technical breakthroughs alone cannot guarantee civilizational advancement. The International Thermonuclear Experimental Reactor Project, known as ITER, provides a perfect example of how cooperation problems can derail even the most promising technologies. Originally scheduled for completion in 2016 with a budget of 5 billion euros, ITER now faces completion dates pushed back to 2034 and cost estimates exceeding 20 billion euros. The delays stem not from technical problems with fusion physics, but from disagreements between member nations over procurement rules, manufacturing standards, and intellectual property sharing. When countries can't agree on basic project management for a single experimental reactor, the prospect of coordinating thousands of commercial fusion plants across the globe becomes almost impossibly complex. Geopolitical tensions surrounding advanced energy technologies create security dilemmas that directly conflict with the global cooperation required for Type 1 advancement. Fusion technology development has become a national security priority for major powers, with countries classifying research that could accelerate global progress if shared openly. China's rapid advancement in fusion research has prompted the United States to restrict collaboration and technology transfer in ways that slow overall development. Meanwhile, Europe pursues its own fusion programs with limited coordination with either China or the United States. This fragmentation means that humanity is essentially running three separate races to achieve fusion power instead of one coordinated effort that could reach the finish line much faster. Resource nationalism could slag planetary energy integration by decades or centuries, regardless of technological readiness. The rare earth elements required for advanced solar panels, wind turbines, and fusion reactors are concentrated in specific geographic regions, giving those nations enormous leverage over global energy transitions. China currently controls roughly 80% of rare earth processing capacity, while lithium deposits for battery storage are concentrated in Chile, Argentina, and Australia. Nations that control these resources have little incentive to enable rapid global energy transitions that would reduce their strategic importance. They can throttle the pace of planetary energy development to maximize their economic and political advantages, turning geological accidents into geopolitical weapons. The European Union's experience with energy integration shows both the potential and the limitations of regional cooperation. The EU has created interconnected power grids that enable renewable energy sharing across national borders, but this cooperation breaks down rapidly during energy crises. When Russia restricted natural gas supplies, European nations abandoned energy solidarity and began competing against each other for alternative supplies. Germany's decision to shut down nuclear plants while increasing coal consumption demonstrated how domestic political considerations can override regional cooperation commitments even during energy emergencies. Competing civilizational models for reaching Type 1 status create fundamental tensions that go beyond simple policy disagreements. China's approach emphasizes state-directed development of advanced energy technologies through massive public investment and centralized planning. The United States relies more heavily on private sector innovation and market-driven development. European models blend public and private approaches while prioritizing environmental sustainability and social equity. These different approaches aren't just alternative paths to the same destination. They represent fundamentally different visions of what a Type 1 civilization should look like and how it should operate. Whether a single nation could achieve Type 1 capabilities independently remains an open question that could determine how planetary energy development unfolds. China's industrial capacity, population scale, and centralized decision-making authority position it as the only nation that might theoretically reach Type 1 energy consumption levels without requiring extensive international cooperation. However, even China lacks the geographic diversity of renewable energy resources and rare earth deposits needed for complete energy independence. The United States has abundant renewable energy potential and technological innovation capabilities, but it lacks the manufacturing capacity and political coordination needed for rapid large-scale deployment. Private corporations increasingly circumvent governmental cooperation challenges by developing energy technologies that don't require international coordination for deployment. SpaceX's space-based solar power development proceeds independently of government space programs, while private fusion companies like TAI Technologies advance their research without waiting for international cooperation frameworks. These private efforts can move faster than government programs because they avoid the diplomatic complexities that slow international cooperation, but they also risk creating proprietary technologies that limit global access to advanced energy systems. The role of multinational corporations in planetary energy development creates new forms of cooperation that transcend national boundaries but also concentrate power in ways that could undermine democratic governance. Tech giants like Google, Microsoft, and Amazon now invest billions in renewable energy development to power their global data center networks. These investments dwarf the energy spending of many national governments and create private energy networks that operate independently of national grids. While this private coordination can accelerate clean energy deployment, it also raises questions about whether Type 1 civilization will be governed by democratic institutions or corporate hierarchies. Climate change pressures create unprecedented incentives for cooperation while simultaneously generating conflicts that could prevent the coordination needed for Type 1 advancement. Rising sea levels, extreme weather events, and resource scarcity force nations to recognize their shared vulnerability in ways that could overcome traditional geopolitical divisions. However, climate impacts also generate competition for habitable territory, freshwater resources, and food production that could trigger conflicts large enough to derail long-term cooperation efforts. The path to Type 1 civilization requires a level of global coordination that humanity has never achieved, involving sustained cooperation across multiple generations on projects that require unprecedented trust between traditional adversaries. Yet there's another dimension to this challenge that most analyses overlook entirely. While we struggle to coordinate energy projects on Earth, humanity has quietly been building infrastructure beyond our planet that could fundamentally change the entire energy equation. Beyond Earth, the Space Colonization Accelerator. Mars missions and lunar installations now operate as testing grounds for technologies that could revolutionize Earth's energy systems. Every permanent structure we build beyond Earth's atmosphere creates new possibilities for energy collection, resource extraction, and technological development that could compress our timeline to planetary energy mastery by decades. Space isn't just another frontier to explore. It's becoming the key infrastructure layer that enables true Type 1 civilization capabilities. Lunar bases represent far more than symbolic human presence on another world when examined through the lens of energy resource access. The moon contains helium-3 deposits that could fuel fusion reactors for millennia, but more immediately, lunar installations provide platforms for massive solar collection arrays that face no atmospheric interference or weather disruption. A solar panel on the lunar surface receives solar radiation at full intensity for 2 weeks at a time during lunar day periods, while lunar night periods could be powered by energy storage or Earth beam power systems. The moon's low-gravity environment enables construction of solar installations with scales impossible on Earth, potentially covering thousands of square kilometers with photovoltaic arrays that could beam power back to Earth or support expanded lunar operations. The energy requirements of maintaining lunar bases create positive feedback loops that drive technological advancement rather than simply consuming resources. Lunar manufacturing facilities powered by abundant solar energy could produce solar panels, energy storage systems, and construction materials using lunar resources rather than expensive Earth-launched supplies. This manufacturing capability transforms the moon from an energy consumer into an energy producer, creating industrial capacity that supports both lunar expansion and Earth's energy transition. The reduced gravity and vacuum environment enable manufacturing processes impossible on Earth, potentially producing more efficient solar cells and energy storage devices than terrestrial facilities. Mars missions contribute to energy resource access through different mechanisms that complement lunar capabilities. Mars has a carbon dioxide atmosphere that enables fuel production through atmospheric processing, while dust storms and seasonal variations create engineering challenges that drive innovation in energy storage and grid resilience. The solutions developed for Mars energy systems translate directly to Earth applications, particularly for remote area power systems and grid stability during extreme weather events. Mars also provides a testing ground for closed-loop life support systems that optimize energy efficiency in ways that benefit terrestrial energy management. Asteroid mining prospects offer energy implications that extend far beyond the obvious value of rare earth elements and precious metals. Many asteroids contain water ice that can be converted into hydrogen and oxygen for fuel, but they also contain materials needed for advanced energy technologies in concentrations far higher than Earth-based deposits. A single metallic asteroid could provide enough rare earth elements to build millions of wind turbines or solar panels without terrestrial environmental impact. The energy required to extract and process asteroid materials in space is offset by the elimination of Earth-based mining, transportation, and environmental remediation costs. Space manufacturing capabilities enable massive solar collection arrays with scales that dwarf anything possible on Earth's surface. The new cohort of space-based solar power companies is trying different approaches, such as using infrared lasers or concentrated sunlight to beam power to solar panels. Building on their previous experience, whether in space or in other fields, they are seeking familiar pathways to success, including starting with minimum viable products. Zero-gravity manufacturing eliminates structural weight limitations that constrain terrestrial solar installations, enabling construction of solar collectors with areas measured in square kilometers rather than hectares. These space-manufactured systems could achieve power outputs comparable to nuclear plants while using renewable solar energy. The energy economics of space-based manufacturing create multiplier effects that accelerate both space development and terrestrial energy transitions. Space factories powered by abundant solar energy can produce goods for both space and Earth markets without the energy overhead of launching materials from Earth's gravity well. This manufacturing capability could produce the components needed for Earth-based renewable energy systems at costs lower than terrestrial manufacturing, while simultaneously building the space-based energy infrastructure needed for expanded space operations. Space elevators and other orbital infrastructure could revolutionize energy economics by dramatically reducing the cost of moving materials and energy between Earth and space. A space elevator powered by clean energy could transport materials to orbit at costs comparable to transcontinental shipping, making large-scale space construction economically viable. The elevator structure itself could incorporate power transmission capabilities, enabling continuous energy transfer between space-based collectors and Earth-based distribution systems. Alternative: orbital infrastructure like rotating tethers or launch loops could provide similar cost reductions while enabling new forms of energy collection and distribution. Whether space expansion counts toward Type 1 civilization or represents a different developmental path reveals the limitations of Kardashev's original framework. Traditional Type 1 classification focuses on planetary energy usage, but space-based energy systems blur the boundary between planetary and stellar energy collection. Solar panels in space collect stellar energy directly without planetary atmospheric filtering, arguably representing Type 2 capabilities deployed at Type 1 scales. The distinction becomes academic when space-based systems provide energy for planetary use, effectively extending planetary energy management capabilities beyond the planet itself. The timeline for space-based energy contributing meaningfully to Earth's energy supply depends on overcoming specific technical and economic hurdles rather than fundamental technological barriers. The challenges of space-based solar power include the high cost of launching panels into space, space debris, and extreme solar radiation. The environment in space has several hazards that could cause damage to solar panels, including space debris and extreme solar radiation, which could degrade panels up to 8 times faster than panels installed on Earth. However, space manufacturing capabilities could address these challenges by producing replacement components in space using asteroid-derived materials. Current projections suggest that space-based energy could provide meaningful contributions to Earth's energy supply within 15 to 25 years if space manufacturing capabilities develop as rapidly as current trends suggest. The key breakthrough occurs when space-based energy systems achieve cost parity with terrestrial renewable energy while providing superior reliability and capacity factors. This economic tipping point could trigger rapid scaling of space-based energy infrastructure, potentially providing 10% to 20% of Earth's energy needs within decades of achieving commercial viability. Space colonization represents far more than establishing backup planets or satisfying human curiosity about other worlds. The infrastructure required for permanent space settlements creates the foundation for true planetary energy management by extending our energy collection and manufacturing capabilities beyond Earth's surface. Space-based solar collectors, lunar manufacturing facilities, and asteroid mining operations collectively enable energy resource access and utilization capabilities that transcend traditional planetary limitations. These capabilities could accelerate Type 1 achievement by providing the energy abundance and technological sophistication needed for true planetary energy mastery. But while we've been focused on these dramatic space-based solutions, something remarkable has been happening much closer to home. The renewable energy the entire question academic. Renewable energy deployment has reached mathematical escape velocity, the point where momentum becomes self-sustaining and reversal becomes practically impossible. The numbers emerging from global energy markets indicate that renewable energy expansion has transcended policy decisions and economic incentives to become an unstoppable mathematical progression that could deliver Type 1 energy capacity within decades. Global renewable capacity additions surged by an estimated 25% in 2024, reaching approximately 700 gigawatts according to the latest international energy assessments. This marked the 22nd consecutive year of record expansion for renewables, creating a growth pattern that resembles exponential rather than linear progression. Solar photovoltaic technology accounted for over 3/4 of these additions, followed by wind at 17% and hydropower at 4%. China alone contributed almost 2/3 of all renewable capacity connected to the grid in 2024, with solar photovoltaic capacity additions exceeding 340 gigawatts, representing a 30% increase compared to 2023. These aren't just impressive statistics. They represent acceleration rates that compound annually and create momentum that becomes increasingly difficult to slow or reverse. The surge in electricity demand provides context for understanding why renewable growth rates have accelerated beyond previous projections. Electricity demand rose by 4.3% in 2024, marking the largest absolute increase ever recorded outside of economic recovery periods. This growth was driven by electricity-intensive appliances, manufacturing shifts toward electrification, and increasing demand from digitalization, data centers, and artificial intelligence systems. Rather than overwhelming renewable energy capacity, this demand surge has actually accelerated renewable deployment by creating larger markets and better economic returns for clean energy investments. Storage technology breakthroughs have fundamentally altered the renewable energy equation by solving intermittency challenges that previously limited deployment rates. Battery storage costs have fallen by 90% over the past decade, while energy density has doubled through advances in lithium-ion chemistry and manufacturing processes. Grid-scale battery installations now provide backup power for entire cities during peak demand periods, while residential battery systems enable households to store excess solar generation for nighttime use. These storage capabilities mean that renewable energy systems can provide reliable baseload power comparable to traditional fossil fuel plants, removing the primary technical barrier that previously limited renewable energy scaling. The economic tipping point where renewables become universally cheaper than fossil fuels has arrived in most global markets, creating irreversible momentum toward clean energy adoption. Solar photovoltaic costs have decreased by 85% since 2010, while wind energy costs have fallen by 70% over the same period. In many regions, new renewable energy installations now generate electricity at costs below existing fossil fuel plants, even when those fossil fuel facilities have already been built and their construction costs have been amortized. This economic advantage means that renewable energy expansion continues even without government subsidies or environmental regulations, driven purely by market forces that favor the lowest cost energy sources. Grid modernization efforts have created the infrastructure foundation necessary for planetary energy management through renewable sources. Smart grid technologies now enable real-time coordination between millions of distributed energy sources, automatically balancing supply and demand across continental power networks. Advanced grid management systems can predict renewable energy output hours or days in advance using weather forecasting data, enabling grid operators to optimize energy storage and distribution patterns for maximum efficiency. These grid capabilities transform intermittent renewable sources into reliable, predictable components of planetary energy systems. The National Renewable Energy Laboratory's assessment suggests that recent legislative provisions could boost annual wind and solar deployment rates to between 44 gigawatts and 93 gigawatts from 2023 to 2030, with cumulative deployment of new utility-scale solar, wind, and storage reaching up to 850 gigawatts by 2030. These deployment rates would need to continue accelerating through the 2030s and 2040s to provide Type 1 energy capacity by 2080 to 2120, requiring sustained political commitment and continued technological advancement. Emerging technologies like perovskite solar cells and advanced wind systems promise to accelerate renewable deployment beyond current projections through superior performance and lower costs. Perovskite solar cells achieve conversion efficiencies above 25% in laboratory conditions, while requiring simpler manufacturing processes than traditional silicon panels. These cells could reduce solar panel costs by an additional 50% while improving power output, enabling solar installations in regions that aren't currently economically viable for renewable energy. Advanced wind turbine designs with larger rotors and taller towers can generate power in lower wind conditions, expanding the geographic areas suitable for wind energy development. Distributed energy systems have fundamentally changed traditional centralized power models by creating millions of small energy producers rather than depending on large centralized facilities. Residential solar installations now enable individual households to generate more electricity than they consume, feeding excess power back into the grid for use by neighboring properties. Electric vehicles serve as mobile energy storage units that can power homes during outages or provide grid services during peak demand periods. This distributed approach creates resilience against system failures, while reducing the transmission losses that occur when electricity travels long distances from centralized power plants to end users. The mathematical progression of renewable energy deployment has reached a point where continued exponential growth appears inevitable, barring catastrophic technological setbacks or coordinated global policy reversals. Global generation from solar photovoltaic technology has been doubling approximately every 3 years since 2016, and it doubled again between 2021 and 2024. Wind energy capacity has grown at slightly slower but still exponential rates, while battery storage deployment has accelerated even faster than solar installations. The renewable energy revolution has reached escape velocity through a combination of technological advancement, economic competitiveness, and infrastructure development that creates positive feedback loops driving continued acceleration. Type 1 energy capacity appears mathematically inevitable within this century based on current deployment trends and technological trajectories. But mathematical inevitability assumes that current systems remain stable long enough for these exponential curves to reach their destination. The existential risk factor. Climate disasters, resource wars, and social collapse could derail our progress before we reach the energy abundance needed for planetary stability. The uncomfortable truth emerging from 2025 data suggests that our window for achieving planetary energy mastery might be narrower than anyone wants to admit. We're simultaneously experiencing the fastest technological advancement in human history while facing existential threats that could derail our progress within decades. The question isn't just whether we can reach Type 1 civilization, but whether we can reach it before the forces of collapse overtake the forces of advancement. Climate change impacts our ability to reach Type 1 status in ways that create vicious cycles of energy demand and infrastructure vulnerability. The year 2024 was the warmest year on record, surpassing the previous record set in 2023, according to the IEA's Global Energy Review 2025. This temperature increase led to a 6% increase in global cooling degree days, which directly increased energy demand for electricity, coal, and natural gas consumption. The report estimates that weather effects contributed about 15% to the overall increase in global energy demand, with temperature effects contributing around 20% to the increase in electricity and natural gas demand. This means that as we build more energy infrastructure to reach Type 1 status, climate change forces us to consume more energy just to maintain basic living conditions, creating a race between energy capacity expansion and accelerating energy demand. The vulnerability of energy infrastructure to extreme weather events creates cascading failures that could set back our Type 1 timeline by decades. Power grids designed for historical weather patterns fail when faced with unprecedented heat waves, storms, and flooding. Solar panels lose efficiency in extreme heat, while wind turbines shut down during severe storms. The energy storage systems we're building to enable renewable energy scaling face thermal management challenges during heat waves that reduce their capacity and lifespan. Each infrastructure failure requires energy and resources to repair or replace, diverting investment away from capacity expansion toward damage control. Geopolitical conflicts present technological setbacks that directly threaten the international cooperation required for Type 1 advancement. The IEA's Global Energy Review 2025 notes that geopolitical risks persisted in 2024, with the main European gas price benchmark doubling by December 2024 from its lows in February 2024. These price volatilities reflect supply chain disruptions and resource access restrictions that slow the deployment of advanced energy technologies. When nations prioritize energy security over efficiency or sustainability, the result is often investment in older, less efficient technologies that provide immediate energy access but slow overall civilizational advancement. Resource conflicts over rare earth elements and energy infrastructure create instability that undermines large-scale energy projects necessary for Type 1 status. The materials needed for renewable energy systems, fusion reactors, and energy storage are concentrated in specific geographic regions, creating dependencies that hostile nations can exploit. Supply chain disruptions for lithium, rare earth elements, and specialized manufacturing equipment can halt renewable energy deployment for months or years. The competition for these resources intensifies as more nations pursue advanced energy technologies, potentially triggering conflicts that could consume the resources and attention needed for peaceful energy development. Social instability poses perhaps the greatest threat to long-term energy projects because these systems require sustained investment and maintenance over decades. The IEA's Global Energy Review 2025 indicates that emerging market and developing economies accounted for over 80% of global energy demand growth in 2024, with China and India leading the increase. This rapid growth creates resource competition and potential social instability that could hinder the international cooperation needed for planetary-scale energy systems. When populations face energy shortages, food insecurity, or climate displacement, political systems become unstable and long-term planning becomes impossible. The concept of civilizational resilience in the context of the Kardashev scale addresses our ability to maintain technological advancement while weathering existential threats. Resilient civilizations can absorb shocks from climate disasters, resource conflicts, or technological failures without losing the capacity for continued development. The IEA's Global Energy Review 2025 highlights that the deployment of clean energy technologies is limiting emissions growth, avoiding 2.6 billion tons of additional CO2 emissions per year. This suggests that investments in renewable energy and other clean technologies can enhance civilizational resilience by reducing our vulnerability to fossil fuel supply disruptions and environmental degradation. The competing timelines of technological advancement versus potential collapse create a critical race where the outcome determines whether humanity survives as an advanced civilization or retreats to lower levels of development. Our current trajectory suggests we could achieve Type 1 status by 2080 to 2120 if technological advancement continues at current rates. However, climate change, resource depletion, and social instability could trigger civilizational collapse within the same time frame. The window where advancement outpaces collapse might only remain open for another 20 to 30 years, after which environmental and social pressures could make Type 1 advancement impossible. Achieving Type 1 status might provide immunity from certain existential risks by creating energy abundance that enables large-scale solutions to global problems. A Type 1 civilization could power massive carbon capture systems, build climate-controlled habitats for displaced populations, and maintain industrial capacity despite resource scarcity. However, the IEA's Global Energy Review 2025 shows that while clean energy deployment is limiting emissions growth, energy-related CO2 emissions still reached a new record in 2024. This indicates that even Type 1 energy capacity might not guarantee environmental stability if we reach that capacity through technologies that continue generating emissions. Rapid technological advancement creates new vulnerabilities even as it solves existing problems. The IEA's Global Energy Review 2025 notes that electricity demand increases were driven by factors including extreme temperatures, industrial growth, transport electrification, and data center expansion. While these developments indicate progress toward Type 1 capabilities, they also create new dependencies on complex systems that could fail catastrophically. Cyber attacks on power grids, failures in AI-controlled energy management systems, or cascading failures in interconnected global energy networks could cause civilizational setbacks that outweigh the benefits of advanced technology. The race to Type 1 civilization represents more than just technological achievement. It's fundamentally about survival in an increasingly hostile environment where only abundant clean energy provides the resources needed to address cascading global challenges. The evidence from 2025 suggests we're in a critical window where the outcome remains genuinely uncertain, with technological advancement and potential collapse advancing toward us at comparable speeds. The question becomes whether we can synthesize all these competing forces into a realistic assessment of when humanity might actually cross the threshold into true planetary energy mastery. The new timeline, when will we actually get there? Current data points toward a convergence window that fundamentally changes previous timeline estimates. Based on all 2025 evidence, when will humanity actually achieve Type 1 civilization status? The mathematical progression of current trends points toward a narrow window between 2080 and 2120 where Type 1 status becomes not just possible, but inevitable if we can maintain our current trajectory without major setbacks. Synthesizing all technological advancement factors into updated timeline projections reveals acceleration patterns that compound annually rather than following linear progression. Global energy demand increased by 2.2% in 2024, faster than the 1.3% annual average between 2013 and 2023, while electricity demand surged by 4.3%, driven by energy-intensive applications including artificial intelligence systems and manufacturing electrification. This acceleration suggests that our energy infrastructure is scaling to meet demand at rates that exceed historical patterns, creating momentum that could sustain Type 1 advancement timelines. Renewable energy deployment provides the clearest indicator of our trajectory toward Type 1 status. The IEA's Renewable Capacity Statistics 2025 shows that with 585 gigawatts of capacity additions, renewables accounted for over 90% of total power expansion globally in 2024, marking a record annual growth rate of 15.1%. The National Renewable Energy Laboratory's assessment indicates that provisions in recent legislation could boost annual wind and solar deployment rates to 44 gigawatts to 93 gigawatts between 2023 and 2030, with cumulative deployment reaching up to 850 gigawatts by 2030. These deployment rates create exponential growth curves that could provide Type 1 energy capacity within 60 to 80 years if sustained. Optimistic scenarios assume that fusion energy reaches commercial viability by 2035, space-based solar power begins meaningful deployment by 2040, and artificial intelligence continues optimizing energy systems at accelerating rates. Under these conditions, Type 1 status could be achieved by 2070 to 2080, driven by the combination of abundant fusion energy, orbital solar collection, and AI-managed distribution networks. This timeline assumes that international cooperation enables rapid technology sharing and coordinated planetary energy infrastructure development. Realistic scenarios account for slower technology deployment and moderate cooperation challenges. Fusion energy reaches commercial deployment by 2045, space-based solar power scales gradually through the 2050s, and renewable energy continues expanding at current rates with periodic setbacks from supply chain disruptions and geopolitical tensions. This pathway suggests Type 1 achievement between 2090 and 2110, allowing for technology maturation periods and the infrastructure development needed to support planetary-scale energy systems. Pessimistic scenarios consider the possibility of major technological setbacks, resource conflicts, or climate-driven instability that could delay Type 1 advancement significantly. If fusion development stalls, space-based solar power faces insurmountable engineering challenges, or international cooperation breaks down completely, Type 1 status might not be achieved until 2130 to 2150. However, even these pessimistic projections suggest Type 1 achievement within this century, indicating that the fundamental technological momentum toward advanced energy systems has become difficult to reverse. Different technological breakthroughs could dramatically accelerate or delay these timelines through breakthrough effects that change the entire advancement equation. Breakthrough achievements in room temperature superconductors could eliminate transmission losses and enable global energy grids that operate at near perfect efficiency. Advances in quantum computing could solve fusion plasma control problems decades ahead of schedule. Conversely, technological dead ends in key areas like energy storage or material science could create bottlenecks that slow progress for decades. The IEA's Renewables 2023 report provides concrete benchmarks for measuring progress toward Type 1 status. The report forecasts that renewables will surpass coal to become the largest source of electricity generation in 2025, with wind and solar photovoltaic each surpassing nuclear electricity generation by 2026. By 2028, renewable energy sources are expected to account for over 42% of global electricity generation, with wind and solar doubling to 25% of total generation. These milestones represent measurable progress toward the energy abundance required for Type 1 civilization. Wildcard factors could dramatically alter these timeline projections through developments that aren't currently predictable from existing trends. Breakthrough discoveries in fundamental physics could enable entirely new energy sources that make current projections obsolete. Artificial intelligence systems could achieve capabilities that accelerate scientific research beyond current possibilities. Conversely, major solar storms, cyber attacks on critical infrastructure, or pandemic-level disruptions could set back technological development by years or decades. The indicators we should watch to track our progress toward Type 1 status include renewable energy deployment rates, fusion technology milestones, space-based solar power demonstrations, and AI system energy optimization capabilities. Progress toward the IEA's target of tripling renewable capacity by 2030 provides a critical benchmark, requiring annual expansion rates of 16.6% rather than the current 15.1%. Fusion energy demonstrations that achieve sustained net energy gain will indicate whether commercial fusion deployment timelines are realistic. Space-based solar power tests that demonstrate efficient wireless power transmission will show whether orbital energy collection can contribute meaningfully to planetary energy supply. Energy efficiency improvements provide another critical metric for Type 1 advancement. If artificial intelligence systems continue optimizing energy utilization while managing the grid coordination needed for renewable energy integration, we could achieve Type 1 functionality with lower absolute energy consumption than traditional calculations suggest. This efficiency pathway could accelerate Type 1 achievement by enabling advanced civilization capabilities without requiring the massive energy infrastructure that previous projections assumed necessary. The convergence of fusion energy development, space-based solar power scaling, artificial intelligence optimization, and renewable energy deployment creates multiple pathways to Type 1 status that reinforce each other rather than competing for resources. This technological convergence suggests we could achieve Type 1 status by 2080 to 2120, decades ahead of previous estimates, but only if we can navigate the cooperation challenges that determine whether these technologies get deployed at planetary scale. The evidence points towards something unprecedented in human history. We might be living through the moment when Type 1 civilization transforms from distant possibility into achievable reality. The question now becomes what you do with this knowledge. We're potentially the first generation that can see Type 1 civilization happening within our extended lifetimes. The fusion breakthroughs, space-based solar arrays, and renewable energy acceleration happening right now could deliver Type 1 status by 2080 to 2120. You're living through the most critical period in human history, the transition from a planetary civilization to a truly cosmic one. Support renewable energy policies in your community and nation. Back fusion research funding through political advocacy and investment choices. Advocate for space technology development that enables orbital energy collection. Your individual choices today determine whether humanity reaches the stars or remains trapped by energy scarcity forever.